Morning, everyone. I'm Andrea Rubini. I'm the Director of Operations of Water Europe. And on behalf of Water Europe and the extra group on digital water system management, I would like to warmly welcome you to the webinar of today, which is Breaking Silos, Building Synergies, Unlocking Water Data Interoperability through WATERVERSE, CyclOps, IDEATION, and EDITO. For a number of years, the water sector has been discussing about digitalization, as you know. And today, the question is no longer whether or not digitalization is needed, but whether, how we can connect the data, the platforms, the different models, and of course the stakeholders and the users to transform the information that we can get from the water and water-related sectors into a better decision and greater water resilience and capacity of decision-making. This challenge is particularly relevant at the time when Europe is implementing the water resilience strategy, in the time when the impact of climate change requires to take actions quickly to prevent and be prepared for any potential future concerning the water sector, and preparing also for what is the forthcoming digitalization action plan for the water domain. Water Europe supports strongly this initiative, and you might know that it has recently highlighted that the main barrier is often not lack of technologies, but the fragmentation of data, the systems and the frameworks of the different models of governance. And then at the end, we've been also discussing quite a few number of times about the matter that if you really want to unlock the full potential of digitalization, we need interoperability, we need fair data principles, and on top, stronger collaboration across sectors, disciplines, and geographical scales. The projects that I mentioned before in the title of the webinar today, you will hear from them. They've been addressing different but high complementary dimensions of digital transformation of the water management. These are from data interoperability up to data space, artificial intelligence, digital twins in the framework of inland waters, and as we experienced it for the European Digital Twin Ocean. If you take these projects individually, they have been generating really valuable results, but if we take them together, they can provide really a landscape of what is truly interconnected European digital ecosystem for water could seems like, supporting better monitoring, forecasting, and on top planning and decision-making capacity in the full water cycle. So then, I think that I've been speaking even too much for this introduction. And said, let me thank the Water Europe Digital Water System Management Expert Group, all the speakers, the projects representatives for their contribution today. I really look forward for an inspiring discussion today and how we can together move from a fragmented data landscape towards a resilient water smart future. So thank you so much. Enjoy the webinar, and I'm happy to pass the floor to Elisa Vaggio, who is the leader of the expert group of Water Europe. Thank you so much.
Thank you very much, Andrea, and good morning, everybody. I'm happy to be here with you and to share with you some of the results of our projects and how we put them together. As Andrea was saying, I'm the leader of the expert group on digital water systems management, and our main focus are on data analytics, advanced modeling, intelligent decision support systems, and also we focus a lot in the last meetings that we have with the expert on aspects linked with data spaces and digital twins. So since we had the opportunity to work together in different projects, we see some commonalities and some way to put everything together, to build like a pipeline that put all these projects together. So we decided to do this. It's something that is relevant for us as researcher, but is also important, we think, at European level, because sometimes the projects, when they finish, they are left on one side, and there is no future for these solutions. But this webinar wants also to show that actually results of different projects may be put together, and we can work together even if we are working in different European projects. So I give the word now to my co-leader Roberto, that will start with the agenda and the first context of the projects. Thanks, Roberto.
Thank you, Eloisa, and good morning also on my side. It's a pleasure of being with you today in this webinar. This is the general agenda of the webinar. So I'm going to introduce each of the speakers of today. After we move with the general concept of the webinar, even though I will go very fast on this because it was really well introduced already by Andrea and Eloisa, and then we go one by one to the project involved. Then we have a session demo and a question and answer session, and the conclusion of the webinar. So moving fast with the speakers, these are the people involved today. First, introduce Gerasimo Ansolatus. It's a senior research associate at the Information Technology Institute of CERT. His work focused on computational mathematics, predictive analysis, machine learning applied to the water sector and critical infrastructure. He was the coordinator of WATERVERSE, so that is one of the projects in our webinar today, and he contributes quite massively in IDEATION project and CyclOps, in particular concerning aspects related to data operation and digital twins. Then we have Eloisa Vargio, that was already introduced. She's a public funding specialist at CETAQUA, Water Technology Center, where she works on research activity in the field of digital waters. She coordinates the IDEATION project, and she is the leader of the Digital Water System Management Expert Group. Then we have Igor Atake. It's an oceanographer and a data scientist currently working as a researcher at the Euro-Mediterranean Center for Climatic Change in Italy. His work focuses on operational marine modeling, ocean digital twin, and application of data science to marine environments. And then we have Franco Crivello. Is a civil engineer with a master's degree in hydroinformatics and water management. He leads the asset optimization program at CETAQUA in Barcelona, working on digital solution artificial intelligence applications for water management. He contributes to IDEATION project as work package leader. And then finally, it's me, it's Roberto Di Bernardo. I'm a senior technical manager, at Engineering Informatica, where I lead the R&I grant office, and I also work as a R&I business developer, specifically in the area of digital governance, smart cities, and digital water. And I was proud to be part of the IDEATION project, WATERVERSE, but also active in other projects related more on smart city side, like Urbrecht, Urban Flow. And I'm happy to co-lead the Digital Water System Management Expert Group, supporting Eloisa on this. Moving fast now to the overall concept of our webinar. The key challenge this webinar started from our challenges that we already know and were already described pretty well by Andrea. So the water system nowadays are increasingly impacted by the climate change, environmental degradation, and of course, as the strategy promoted by Water Europe, implementing the water smart society, consider the digitalization as a key element to support the sector. So improving stakeholder decision-making and operational capabilities. In this specific aspect, digital twin AI represent clearly key tools to support and improve the sector, in particular increasing the efficiency and the effectiveness of it. However, for a key implementation and effective implementation of this solution, fragmented data is a clear barrier. In this sense, the European Commission is pushing a lot on increasing the capability in terms of interoperability, in particular via the European data strategy that calls for the implementation of sectorial data spaces. But even more, to open the opportunity for cross-sectorial data spaces. In this sense, interoperable data infrastructure for sure, and semantic integration for sure is the way to go to put in place fully operational AI and digital twin, in particular if we consider the world of inland water sector. In particular is also a key element, the European digital infrastructure, because on this, if we manage and can leverage their capabilities, this for sure will help the implementation or full operational inland water, supporting the local communities, capitalizing the effort, investment, and offering, of course, computational capabilities. Within this webinar, we are putting together, as mentioned, following this approach, so leveraging interoperability and data pipeline capabilities. We put together four projects that have common ground on considering water domain challenges, use technologies, and data centrality. These projects are WATERVERSE, that focus on efficient data management in the water sector, CyclOps, focusing on AI operation and data operation pipelines across the several sectors, considering water among those. IDEATION, that is a CSA setting the roadmap towards the future digital twin for inland waters that in order to be compliant, interoperable with the digital twins of the ocean, and then the EDITO, so the European digital twin of the ocean, that is the core infrastructure of European digital twin ocean. And for this, along this webinar, you can see how different projects that were not meant at the beginning to work together, thanks to unlocking the data interoperability, can exploit even better the result, having a multiply effect. With this, I don't want to spend more of your time, so I will pass the floor immediately to Gerasimos.
Thank you, Roberto. Good morning, everyone. It's my pleasure to be here and start presenting the WATERVERSE project and the CyclOps after that. Next slide, please. A few words about the project. Okay. WATERVERSE was a 3-year Horizon Europe Innovation Action Project under the topic Data 0103, Technology for Data Management, running from October 2022 to September 2025. It had a budget of just over 5 million euros and brought together 17 partners from 10 European countries with multidisciplinary backgrounds, and this diversity of partners, utilities, and pilots is what allowed us to test our ideas against the different real-world operational conditions. Next slide, please. Our mission was straightforward but hard to achieve. It is to develop a water data management ecosystem that makes water sector data management accessible, affordable, secure, fair, and easy to use. In order to achieve this, we engage stakeholders and co-create a solution at the early beginning of the project, involving 3 multi-stakeholder forums rounds, implementing and demonstrating the WDME and the fairness ecosystem in which fostering to assess the data and metadata against fair and Meloda 5 principles, and validate this framework into 6 pilot sites in 2 iterations, and of course ensuring security, energy efficiency, and securing the long-term viability of the ecosystem. At the right hand, you can see an overview of high level architecture, multi-level architecture of WDME. At the beginning, in the data collection and federation layer, consists of tools that enable to collect data through different sources and through APIs, and also have tools to produce synthetic IoT data. Once the data is collected, it is passed to the next layer, which is the interoperability and data harmonization layer that is responsible to harmonize data according to smart data models and water-related ontologies, and in order to transform the data into standardized format, in particular in HCNGS ILD format. Then we have a data management and a storage layer, which is responsible for storing and distributing the harmonized data to other components. The data pre-processing analysis layer includes modules that allow us to validate, clean, assess the data, anonymize, cluster, and assess the quality of the data. And also is a layer that includes some specific services and modules that develop in order to cover the specific needs of the pilots. For example, to predict the chlorine concentration, to predict the floods, or analyze satellite data for monitoring water quality. At the top layer, we have the application layer, which is a composite services in order to interact with the users and visualize the results. And as a cornerstone of the WDME is a data preparation pipeline editor module, which is acts as an integrator and integrate all these services and allow us to prepare pipelines and schedule and execute periodically these pipelines. Next slide, please. I stay and explain a little bit two cornerstones. One is the data quality assessment framework. The water organization manages data from different diverse sources, systems, and very often are poor quality that affects the analysis and decision making, reducing the reliability of results and stakeholders' trust in them. So we propose a DQA, data quality assessment framework, that runs as a continuous loop, and we start from the data ingestion and governance, specify some rules for ownership, access, and quality expectations, and then automated assess the data across 5 dimensions: completeness, consistency, timeliness, uniqueness, and validity, and then improve the quality of the data via the data validation and reconciliation tool. If we find problems with missing values, outliers, rule violations, etc., and then reassess the quality of the improved dataset. And this continues until we receive a high quality dataset. It's okay. This work has already published in Cambridge Prince Water journal. Next slide, please. I'll give you yes, this is a short a screenshot from the data pre-process pipeline editor, where this tool, this process that I explained previously, integrated into the WDME and validated into a Spanish pilot. I think the key takeaway of this slide is that all these green, yellow boxes are configurable services, and so no developers can easily connect together and without writing specific codes and difficult programming codes. Next slide, please. So the second, let's say, result of the WATERVERSE is a fairness ecosystem. Everyone talks about making data findable, accessible, interoperable, reusable, but in the water sector, this is that aspiration usually stays abstract. In the WATERVERSE, try to make it concrete and sector specific. We build a fair by design ecosystem in order to enabling trustworthy, interoperable, and reusable water data. This ecosystem consists of 5 pillars: standardized fair implementation profile that translates fair principles specifically for water dataset services and entities. Fair alignment, smart data models extending DKTP, NGSLD, and the domain ontologies for real semantic interoperability. Then we have a fair digital object enriched with persistence identifiers and machine actionable semantics. Then publish the data metadata and DKTP catalog for discovery and reuse. And finally, we have integrated 18 fair services for automatic assessment, validation, enrichment, and publication and across the full data lifecycle. Next slide, please. Again, is how we run these fair services. How can create a pipeline using some of them. Roberto, some clicks because it's not so easy to identify what the box is written there. Okay, first block, for example, is in order to, if we want the user want to create a new data model. So we have the services that assess the data model during its creation, and then also evaluate the model against the WATERVERSE FAIR principles, guidelines, and then also have a data quality assessment tool in order to assess the data. And the other blocks, if you click two more things, I think one more, yes, okay. If you want to find an SDS, a smart data model, then you have for the data set that ingested in this pipeline, we use this service in order to retrieve the schema and make the expose machine readable semantics for the data model, and then validate the model against predefined rules, ensuring compliance. And at the end, compliance with standards and regulations. And at the end, all this assessment combined, merged into a report that provide to the end user. Next slide, please. So now, as I said before, WATERVERSE was validated through 6 real-world pilots across Europe involving 2 evaluation cycles. And in that pilot, operators used the WDME dashboard to monitor chlorine levels and predict treatment impacts. And we managed to reduce the data processing effort by 35 to 45% and improve monitoring effectiveness by 20 2030. In a German pilot, digital village twin integrate fragmented sensors and rainfall data for flood protection, reducing both data preparation and forecasting time. In a third pilot, we put together telemetry data, smart meters, consumer reports, and satellite data into interoperable environment, harmonize, anonymize, process the general data, and fed again the digital twin in order to make simulations, for example, for state. And then again, we managed to reduce preparation time and cost saving with the ME-based workflows. Next slide, please. Next slide. Okay. In pilot, the UK and the Southwest Water tackle combined sewer overflows, systematically collecting, validate, and cataloging data that had been scattered across multiple systems, and again, cutting labor effort and reducing erroneous data up to 35%. In Hydralia in Spain, we harmonized data from many external and internal sources and support integrated water cycle management dashboard. And in final pilot, we automated the transformation of heterogeneous to standardized format, replacing manual conservation work and cutting both effort and operational resources up to 50%. Next slide. So in general, the impact that we received from the pilots prove measurable time saving in data processing, resulting in lower cost and reduced complexity. We have a 35% reduction in manual data processing, a 24% reduction in latency before data was ready for analysis. We managed to reduce the detection time by 25 to 40%, and even a rough 50% cut in computational and energy requirements, because we have a faster processing and less data duplication and more efficient execution workflows. So next slide, please. A key lesson learned is summarizing 5 standout. First, this is the true interoperability is a core challenge, and it's not just about the standard. It's WATERVERSE showed that the real world interoperability goes beyond standards, requiring flexible system integration, semantic harmonization, and effective alignment with legacy infrastructure to enable scalable water data spaces. Second, FAIR is achievable, but it requires real tooling and dedicated data stewardship roles. Third, the metadata quality goes hand by hand with data quality. Without the good metadata and data, water utilities can't trust or reuse the data. Fourth, clear governance and liability frameworks are what actually unlock people's willingness to share. And the WATERVERSE confirmed that clear governance and liability frameworks are essential to build trust and unlock data sharing and reuse in the water data ecosystem. And last, stakeholder co-creation is important from the early stages and continuously involved in all the phases of the project, the development. And this is what drives to the adoption of the solution and uptake the solution after the end of the project. That is for WATERVERSE. Now move to the CyclOps. Next slide, please. One more. As you can see, CyclOps is WATERVERSE is focused on the water sector, but CyclOps is domain agnostic and aiming to provide tools for automated end-to-end data life cycle management for fair data integration, AI, and machine learning processing and reuse across domain and across data spaces. A few words about the CyclOps is a 3 years research and innovation action project under the topic Data 0 and 02, running from January 2024 to December 2026. The budget is roughly 9 million euros with 24 partners for 11 countries working in this project. So, yeah, next slide, thanks. Our broader aim is to facilitate the adoption and the production of data models and services from and for data spaces so that AI-based data-driven applications become accessible to everyone, business and research alike. Our objective is to provide interoperable, trustworthy, and secure automatic management, governance, and maintenance of the entire life cycle for a large-scale volume of data coming from heterogeneous distributed sources, from data spaces, from data lakes. The thread connect both simple to enable real data sharing and exchange within data spaces. CyclOps is essentially the automation layer that makes data spaces practical to operate at scale. Next slide, please. Yeah, this slide is try to show the heart of the architecture. As I said, we receive data from data lakes, from data spaces like a green deal data space, tourism data space, procurement and manufacturing data space. These are the main use cases. But here you can see how to work in the water sector. CyclOps sits in the middle and consists of the interoperability layer that handles making heterogeneous data speak with a common language. The knowledge layer that adds semantics content through knowledge and knowledge graphs. The runtime layer consists of the DataOps that provides an automated framework for managing end-to-end data pipeline, encompassing data ingestion, discovery, curation, quality assessment, and pre-process and analytic and pre-process the data. And then AIOps consists of the tools that are responsible for analysis of the data and create AI and ML pipelines. And the data execution and abstraction component enables to distribute data processing and analysis by providing a set of data abstractions and processing kernels that support the development and execution of AI-driven tasks. Then user intent layer is a layer that user express what they want without needing engineering the pipeline by hand. I mean, we automatically translate the intent of the user in natural language into pipeline creation and generation and then execution. So next slide, please. The impact, here try to summarize the impact of CyclOps across 3 dimensions. Scientifically, CyclOps enables unconstrained exploration beyond individual domains thanks to its generic architecture, improves data spaces and knowledge graph technology to enhance automation, security, accessibility, and support human-centric approach to data integration. Economically, it democratized participation in the data economy, facilitates new data-based value services, and strengthens EU competitiveness through data. And societally, it boosts workforce skills and creates demands for new professionals and roles, while public trust in data system and engagement in the digital economy. Building trust. So yes, thank you. That's all from my side. Thank you.
Thank you, Gerasimos. Many thanks for this presentation about WATERVERSE and CyclOps.
Thank you.
Now is the turn of ideation, so I will give the floor to Eloisa.
Thanks, Roberto. Yeah, ideation is about inland water in the digital twin ocean. And I was the coordinator of the project, but also engineering, CERT, and CMCC were involved in the project. So it's a pleasure to be all together today. IDEATION was founded under the Emission Ocean call. That was a coordination and support action. It was a short project, let's say, in 2 years, and it just finished in May. So we are now preparing the final document, but the project is already finished. And it was a small consortium of 11 partners. Next, please. So the idea of the commission when they launched this call was to put together ocean inland, in the sense that already 5-6 years ago, they started an initiative regarding the digital twin ocean. And in this phase, 3 years ago, they published a call asking for the connection of inland waters into the digital twin ocean. So is where IDEATION came. And so what we do since it was a coordination support action, our intention wasn't to have a digital twin or digital twins for inland waters, but to prepare the road for having this in the near future and having it connected with EDITO. So we analyzed the problem according to a divide et impera approach. So we divide we consider the different kind of inland waters that are snow and ice, reservoir, lake, wetland, urban water, river and estuaries, coastal water, and groundwater. So we studied each of them separately with support and great support, let's say, of the many stakeholders around 18 countries. Next slide, please. The main results of the project are the 3 that I'm going to present. The 4 that I'm going to present. The first is the so-called open keywords. It is an inventory of 6 catalogs that has been collected during the project. One catalog is about policies and regulations, another about European funded projects, then another regarding scientific results. Then we have tools and technologies, open data and sensing sources, and finally a catalog on meteorological database. Since the collection of this data was very huge, that was unexpected when we prepared the proposal, we decided to have a smart way to interact with these catalogs, that is a chatbot. The chatbot is already running, is an LLM-based chatbot that will be available online as soon as we will receive the okay from the reviewers of the project. So in September, the Open Keywords chatbot will be available for everyone, and it will be used for different steps in the development of a digital twin for inland waters. So next slide, please. Even if our project is a coordination support action, so we have not real pilots, we decide to have some use case as a reference in order to concretize more what it is expected for each of the inland waters. So we selected, according also to the experts that are in a consortium, 8 different scenarios in 7 different countries. So we studied the river and estuaries in Greece, the wetlands also in Greece, the reservoirs in Cyprus, the lakes in Italy, the snow and ice in Switzerland, the groundwater in the Netherlands, the urban water in Spain, and the coastal water in the UK. So for each of them, together with selected stakeholders from our network or some water-oriented living lab held by by Water Europe or from some projects that we were in contact with, we co-create these reference use cases. And then we also interviewed other stakeholders to check the possibility to replicate those case studies, use cases in other conditions and in other scenarios. Next slide, please. Another relevant result of the project is, of course, the reference architecture that is based on other architecture that, for example, the one that has been done for the digital twin ocean, and we divided it in different layers to cover the different aspects that could be relevant for the development of the digital twins, and in particular to be compliant with the digital twin ocean. We have also a connector, direct connector with the EDITO, that is the digital twin ocean project that then Igor will present, and also with the destination Earth. So we have this everything together, let's say, and in the project we also demonstrate that this interoperability is this compliant with EDITO and the Destiny is true, because we defined 3 proof of concept that we put in practice. Next slide, please. The final result, final for this presentation, but final as also as a result of the project, because it arrived at the very end of the project, is the roadmap. So it is a guideline to say to the future developers of inland waters, digital twins, how to proceed. So first of all, of course, the selection of the inland water, depending on which is the context, which is a scenario, which is the client that is asking us for a digital twin. Then we have to start talking with the right person. So we have to identify the right stakeholders that know very well the situation, the data that are available, the requirements, what is missing, which is really useful for that scenario and what is not, and this kind of thing. So the first step after having this talk with stakeholders is to collect business requirements and user requirements. Starting from that, it is possible to define the use cases, and also to have a vision more to the future. We perform also strength, weakness, opportunities, and threat analysis to check which are the potentiality of having this digital twin developed, and which can be the weakness and the threat that can somehow don't allow the real implementation and the real deployment of the digital twin. After the definition of the use case and this analysis, we have also the technical specifications that will be used for the real development of the digital twin. In particular, following the recommendation of the technical governance that we defined under the umbrella of the project. And also we have a very, I mean, like a manual, like a guideline with several technical guidelines. So also the technical guidelines should be followed during the development of the digital twin. And then, since we have this reference architecture that is very general and can be applied to different situations, we have to characterize it explicitly for this case that we are considering. And once the reference architecture has been characterized, we also suggest in our roadmap to perform 2 kinds of assessment, one technical and the other one more related to the life cycle. So the technical core assessment consider all the tools and the application and the sources that has been identified as part of the of the digital twin, and then an assessment on the life cycle and the life cost should be applied to see if, the effectiveness of the solution and how the solution can be then really deployed in the field. And so at the end of this road, the digital twin of inland water has been defined, and so it will be developed and deployed in the real scenario. That's it for my side.
Thank you. Many thanks, Eloisa, to give this overview. As we can see, we will be able to see later, its ideation is a sort of envelope that will allow all the project to stay all together and support the implementation of digital twin, or the inland digital twin, even in the experiment we did. I now pass the floor to Igor to introduce EDITO.
Thanks, Roberto. Thanks, Eloisa and Gerasimus for speaking before me. And now I'm going to talk a little bit about the ocean part, let's say, so how we connected what was originally thought for ideation in the EDITO world. And before showing the specifics of this connection, I'm going to introduce a little bit about the EDITO itself and what one can do with this European digital twin of the ocean. So I think the first note, the takeaway from this is you cannot experiment on the real ocean. So if you are trying to understand or assess a storm, a noisy event, a heat wave, you cannot do experiments over there. So you need a sort of platform, modeling, data in order to gather all of these elements and then try it by yourself on different manners. So I think beyond this experimentation scenario and framework, EDITO is also built for everyone. So it is meant for people that are working in the blue economy, scientists, NGO modelers. So at the end, it's not just a place for experimentation for a specific niche of people working with the ocean, but for every type of people. So I think that's a real good implementation of EDITO that's capable of gathering different type of people. So with it, you can explore data, you can run models, and then you can create what-if scenarios using the tools that are available inside that platform. So next, please. So what this image represents one of the modes of EDITO. So basically, the platform is created around these three verbs, let's say. So it's exploring, creating, and contributing. So by exploring, you can explore real data that are available inside the platform. So you have not only data, but also even data generated within the EDITO itself. So you're not relying only on data that is arriving, but you can create data and also deploy over there. And the part of create is not only data, but you can also contribute with your model or service. So it's possible that you can develop an application. And once you think that's on a mature point, you can contribute to the platform, pushing it over there. So not only your usage, but you can also be contributing to the others to be accessing what you have developed. And that's something that we've done in this connection between ideation and EDITO. We actually created and contributed to the platform, pushing the proof of concept from the inland digital twin to the ocean digital twin. Next, please, Roberto. So here I would like to highlight just a little bit about the data and the compute part. So as I said before, we have different types of data available in the platform. And we have all the Copernicus marine data sets available there, sort of physics, biogeochemistry, the forecasts. And we also have a ModNet, so the European data network and available all within the EDITO ecosystem. So you don't need to gather all the pieces on different places and put it in there. So they are ready for consumption and usage and most of the services and tools available in there. So there is also a data lake. This is everything on cloud. I think it's very important to mention. So all the ecosystem is a cloud-based architecture. So it's very optimized in a way also to build and avoid long queues, long time waiting for data consumption. So this data lake, it's very important in the whole architecture. Otherwise, you can have a lot of data, but if the access to it is very slow and takes a lot of time, then you're actually creating thresholds that you do not want when you're trying to explore and utilize that platform. And not only that, but you have also compute capabilities within this cloud itself that using also the HPCs all around Europe with not only CPUs but also GPU integrated. So you have also space for exploration, of course, with limited resources, but if more is needed, it is possible to get in touch with the platform, the people working in the project that's still ongoing since 2019, 20, if I'm not mistaken. It's aimed to be continued in the future. Next, please. And here is the data lab. So beyond the data part, we also have these and let's say kind of a dashboard where people can get access to all the services and processes within the EDITO system. So here is repeating a little bit the modes that I just mentioned. So we have the explore, create, and the contribute boxes. And when you click, you will receive more information about what is going on behind of each box, how you can really understand what's your aim within the platform. So are you a user that will be mostly exploring, or are you a type of user that you want to really contribute to develop and deploy things into the platform? So it's I just put on a screenshot because the possibilities on Data Lab are enormous. So I didn't want to spend a lot of time here. But in the next slide, I show a bit more in depth what we are what happens when you already have a goal. So please, the next slide. So here we can look for services or processes if the person that's using knows what wants to see. So here's an example that we are doing a query to find the ideation proof of concept. So with these search capabilities, you can find, for example, if you don't know what you need, we can use the search bar to see if there is something that would suit your problems or your questions. And then you can, in this case, it is a service, so you can open it and you can even configure it if needed. There is also these possibilities, and that will run on your browser. So you don't need anything else. I think that's one of the major advantages of having such an architecture system, that if we were talking about the modeling and proof of concept in the past, you would need to have a lot of things on your computer. You need to have the compute capability to test that on your computer. And with EDITO, you simply click and then you're ready to go if you have internet connection. Please, next slide. And here, basically, was the configure capabilities, but that's for advanced users. So it's just showing that EDITO is for base level users, but also advanced ones if they want to explore more, do a deep dive within the application. Next one. So can you push it again? Maybe you have a video here. Okay, great. So now I'm going to talk a little bit about the SIMCC applications. So we worked intensely in EDITO in the past. So we deployed models, focus applications, what-if scenarios within the platform. All of them are available. So in the bottom, you can see the three major models that we have in-house that are available in there, and other institutions also developed and deployed focus applications, what if scenarios that are still available in the platform. And here I would like to show you with this video one of these applications. We will be showing another one, but this is a focus application on oil spill modeling. Can you click on the video, Roberto, so you can see if it launches? No, didn't launch. Or maybe if I share it from my computer, maybe.
It's moving to another window, so I try to show it now. Just a moment.
Okay.
I don't know if you can see.
Yes. So basically here we have an example of this cloud application in which we are showing the with oil, which is where is the oil application, where we let the users choose locations anywhere in the world, choose any date in the past, or also forecast when we have data available. And with that, we can launch oil spill simulations and observe the results and the platform itself. So this is a simplified front end, and so users can input the information. So we didn't want it to be very knowledge based. So anyone in theory with a little bit of knowledge of the sea could launch an oil spill simulation and do a lot of what if scenarios. So here we are showing an oil spill simulation result in Gallipoli area in south of Italy. And here we have all the results of this simplified oil spill modeling. We have the animation. So this, if you didn't have this application, in order to do a simple test, like what would happen if an oil spill happened in my coastal city, in a place I want to take vacations on. So all of this with these cloud capabilities and abstraction of the computation elements that you need to do such test, they are gone with the capability of having everything cloud-based installed. So this is a very simple example of what people can do with this platform. So this is one of the focus applications available within EDITO, and we'll be showing more in the next proof of concept. And that's my final slide that I'm just wrapping up. What is EDITO? What was built within, how CMCC also contributed to this platform, and then how we managed to create this integration from the inland to the marine part. So I think this is something very important that we need to take into consideration, because sometimes we split disciplines, we split domains, but at the end, the inland and the coastal waters, they are one thing. They are not only resources, but they are the environment for species, environment for people. So we need to bring them together. And I think this is one of the initial steps that we are doing. We're bringing these different disciplines into a single framework. So with that, I pass the word to Franco. And thank you for your attention.
Thank you, Igor. Now it's the floor of Franco.
Thank you, Roberto. Thank you, Igor, and then the other speakers so far. And with me, we will see the projects in action, as this is the title of the webinar, Breaking the Silos. We will see how these 4 projects that we have seen so far, they can work all together in order to solve a real challenge of the world, as it is the contamination by microplastics over the sea. So how did we do this? Our objective integrating the different projects was to estimate the amount of plastic that reaches the sea through the Aliakmon River, which in fact the Aliakmon River is one of the RUCs that Eloisa presented before. It's a reference use case developed under the IDEATION project. Well, estimating this amount of plastic after a specific storm event. And the approach in order to do this was to develop a very simple distributed hydrological model, implementing the soil conservation service curve number method developed by the Americans, and the synthetic and utilizing a synthetic unit hydrograph for calculating the runoff discharge at the mouth of the river. This was done for the lower basin of the river. Then in a next slide we will see how it was done this. And I have to here I have to do a clarification for the more technical hydrological audience. I would say that the model wasn't meant to be the most accurate hydrological model for the river. The model was just was the idea to prove the concept that all the different projects can work on together in an interoperable way, and making them able to produce something real and useful. So you will see that the model lacks of calibration, and some of the parameters were assumed, but because this also to develop a real hydrological model demands a quite amount of work. So just to clarify that. On the other hand, I want to say that the framework that we develop with the WATERVERSE, CyclOps, and IDEATION, it is replicable in any other catchment, as it is a very common problem. This one, I think it's a very useful. You only have to, of course, after obtaining the data that you need for running the simulation, you only have to adapt your hydrological model, or even make it, improve it, or something like this. So it can be adopted in different geographical regions. And finally, the model utilizes open data sources, two in particular that we will see in the next slide. But it is there is a bigger potential for including other open data sources, and also in order to make them update from time to time, like with a specific frequency. So this is like converging this model into a real digital twin, which can be updated, and someone doesn't have to reopen and rework all the work that has been done so far. So yeah, the flow of how it works, everything is the one that you are seeing below the screen. First, the WATERVERSE, and through its water data management ecosystem, they took the inputs, the data which is necessary for running the simulation, and then with CyclOps, WATERVERSE do this pre-treatment, and then with CyclOps and IDEATION, it is run the simulation through this pipeline, AI pipeline for running the simulation. Finally, the results that we obtained here, which is the specific discharge for this river in concentration terms. These are used by EDITO, and thanks to the What If application now, which is already available online. This application took this information and runs the simulation to see how the macroplastics disperse over the sea for a specific time frame. Next slide, please. Thank you. Well, and here I want to comment a bit about how the hydrological model was developed. First, well, of course, we have to find our case, as I mentioned, this is the Aliakmon River. The picture that you are seeing right now is Greece. And thanks to the first open data source that we used, it's HydroSheets, where probably some of you have already known about it, have already here. From here, we obtained the shapefiles and some information and characteristics from the river basin in order to obtain this information regarding the boundaries of the catchment and so, as well as the rivers. Next slide. Once we have defined this, we decided to divide the catchment in three and perform the modeling for the lower subcatchment, which is highlighted in light green. And on the other hand, we have the other two subcatchments. The upper subcatchment is the Almopaios River, it's a tributary from the Aliakmon River. And the lower subcatchment, which is actually the bigger one, the biggest, it is the Aliakmon River, but at the end, it ends in the Polyphytos Lake, which is an artificial lake built by a dam. So the outflows of this subcatchment and this lake are regulated according to the necessities of the people. Thus, we did this in order to apply as accurate as we can the SES model, as there are some restrictions regarding the size of the catchment where you can implement the hydrological methodology. So we used this, and we used the inflow from the Polyphytos and from the Almopaios. We assumed values here, but this can be easily obtained by the authority asking them to the information, of course. Next slide. Then from this, for this catchment, we used the ERA5 land reanalysis data for obtaining the precipitation. And for each cell size of the precipitation, we calculate the effective rainfall, effective precipitation, as you well know probably that all the rain that comes from the sky doesn't reach the river at the end. Some of its part it infiltrates into the ground. So we use this in order to calculate the final runoff. Here we use this synthetic unit hydrograph in order to obtain and to make this addition. Once we obtained the final hydrograph, we assumed a specific concentration of the macroplastics in order to calculate the final concentration that will arrive to the sea. Next slide. Once we have this final concentration, we use it in EDITO, well, in the service it was developed, that we will see now in the demo how it works. And here you can see a screenshot of the dispersion of the macroplastics. Next slide, please. And then before to pass to the demo and the last section of this webinar, up to now I explained how the hydrological model it works, but in order to give you a very simple idea of how is the pipeline of the information between the different projects, we start with the information with the data that we need, the ERA5 data and the HydroSheets, which actually the ERA5 land data belongs to a specific storm event on the 9th of January of 2019. And with this information, the HydroSheets, this was used by the water data management ecosystem in order to do a harmonization and standardization pre-processing. Also here, the trimming between the precipitation data and the basin was done, among other pre-processing tasks. This was all updated to a SICAM, and was used by the CyclOps AI pipeline in order to run the simulation. for finally obtaining the plastic discharge, and also, of course, everything in this all these different elements can be held by the reference architecture of IDEATION, and then with the plastic discharge, this was used in EDITO through the METS leak to Lagrangian model, as Igor mentioned it before, in order to perform the simulation. So yeah, that's from my side. The next slide will be the demo. Roberto.
Thank you. We are now sharing the screen for the demo.
I think there is no.
The audio is not
Yeah,
working.
the audio.
So I suggest, sorry for that. I suggest to start again, and probably Gerasimos may talk over the WATERVERSE and CyclOps, and Igor over the EDITO part. And we have also the subtitles. Sorry.
Do you want to share my screen? Try.
Okay, try first you, and if it's not working, just talk over it.
I send a request to share. No, you should close the sharing. Could you close the sharing? Because I cannot share.
Jana, Tiffany, can you stop the sharing? Okay.
Okay.
Thanks.
Oh, I cannot share the sound. Maybe. No, give me. No.
No?
I have the option is inactive. The option to share the sound.
So you have to speak
So it's
over.
Can you share the video, Gerasimos, and talks a bit on top of it? Sorry for this issue.
Not having the rights to.
At least to share. Okay.
Can you see? Can you hear
Yes.
the
Yes.
sound?
Yes.
Yes, yes.
I can hear you. Not no, the audio, no.
Okay.
So you have to speak over it.
Oh. Okay, here you can see the demo at a glance. We have take the data from the WATERVERSE, ingest and preprocess and standardized. Then, sorry, because I heard the voice of the video. So inside the WATERVERSE, the first we establish the data connectors in order to receive the data, then go to the mass apparatus. Here you can see how the user registered in the WATERVERSE using the credentials. And each organization has its own environment, as you can see here. And then here we can see how to identify the resources, data resources, and add the datasets into the WATERVERSE data portal. It's a second instance. Then here can user can prepare the pipelines. So I'll upload the data from the second instance from the data connectors. Here we have two different resources, data from the different resources. And then convert it with this operator to convert the data into NGSLD format. So with the clipping operator is a custom operator that can merge the dataset and homogenize into NGSLD format. And the output push again to the SICAN instance. And in this screenshot, we can see how to schedule the execute the pipeline periodically. We have different options. Here we can yes we can and here we can execute the pipeline and specify where in SICAN the output will be stored and in which method. Of course, here we have hide the API keys because it's confidential. Yeah, here we specify the organization and the dataset. And start the process in order to execute the pipeline. And here you can see the outcome of this process that's stored in the SICAN. Now, in the CyclOps, we receive the data from the SICAN and use these tools, these steps, we analyze the data based on the models that Franco presented before and then store the artifacts into a menu, an ML flow, and then push the again the result of the analysis into the data portal. Yeah, here is the environment of the CyclOps lab. The CyclOps lab contains a lot of tools and functionalities. Here you can see how to create a pipeline, starting from fetch the data, then create the code in order to calculate and make the estimations, the calculations, and execute the pipeline. Then, okay, we try to run the pipeline. We set up make some setups, and the pipeline has executed. And go to the model storage, the IO, in order to see the results. And here, every experiment is stored, and also provide some metrics about the performance of the process of the experiment. And the fifth stage was to push the data in the WATERVERSE data portal. And then maybe I ask Igor to explain.
Okay. Okay, so now we have the application that I just mentioned. So we have this proof of concept between the IDEATION and EDITO connection. So here we did a plastic parcel example. We're using macroplastic in the Yakima River input. So Franco explained a little bit the methodology before. So here we have this, again, this web application where we are showing the area of interest, which are the modeling chains that we decided to use. So we also created from using Surf-Hyphen this hydrodynamic modeling in the area, and then we aim to compare what would be the case using Copernicus Siemens dataset directly with this Surf-Hyphen modeling and hydrodynamic modeling to see how the plastic simulations would differ among these two datasets. So we have the same simulation setup of microplastics in the Yakima River. And in the left panel, we have the Copernicus marine data from MedSea, and in the right, usually the results for this hydrodynamic modeling. And so here we're exploring the results from Mathlete 2, and then we can compare also the mass balance, showing where we have coastal or not coastal plastic or surface. So basically, in the results we achieved is saying that in the Copernicus marine data, so the regional data set, that it's okay for you to launch a simulation, it will work, and did not represent properly the plastic was actually beaching more. On the other hand, when we're having high resolution modeling, the plastic was going further south. It was more available in the water column. So I think this was an exercise to highlight the difference between the tools that you use to do the modeling, that they will provide you different outputs, and which one is more adequate for each situation. So here, considering we have a river, we have an estuary, it's much more likely that you prefer the high resolution modeling rather than just the regional modeling. And in EDITO, we have all of these components ready to be integrated and merged. So here we can show what we can achieve with a simple modeling tool that we just want something to be more or less knowledgeable what is going on. And then we have a more specifically detail-oriented simulation in which we really achieve a more proper representation of the oceanographic features that are happening in that bay. So I think that's it. That was the idea behind this ideation and EDITO proof of concept.
Many thanks, Igor. Many thanks also to Gerasimos to jump into this this part. Thanks, Franco, and sorry for the audio issue, but I do hope you enjoyed anyway the demo. Thanks to the really good explanation from our colleagues. And now it's the time to go fast towards the conclusion because time is over. Let me share this screen. Just a second. Okay, so I would start with just one question that will drive us towards the conclusion, and the question is for Eloisa, because it's about ideation that was, as you saw during the flow of this webinar and the demo, it was a sort of envelope through which we put together the results of the project, connecting in the end inland water with the ocean. So the question is, now that the project ended, what are the key recommendations that you would give to those that are planning the development of digital twin for inland water in the future?
Thanks, Roberto. And yes, I think that ideation was like the envelope of this, but then at the same time, I think that recommendation can be more general, that can be also applied for projects like WATERVERSE, CyclOps, EDITO, and other technological at least projects. In ideation, we collected several recommendations from several points of view. We started from the stakeholders because we had a very long way that we worked together with the stakeholders. We also made a socioeconomic assessment. We study with Codefine, as I said, these reference use cases. So the stakeholders were always involved in our activities. And one is, I mean, is not probably is not exactly a recommendation, but is of course a lesson learned that without stakeholder we cannot define a solution that then will be adopted in the real life. And so this is the first. Then of course we have more recommendation that came from different perspectives, the technical governance, the technical guidelines, also what we learn from the core assessment and in this kind of thing. And but I mean, I think that one recommendation that is more for the European Commission probably is don't. I mean, we are breaking silos, so don't create silos. No, they started with the ocean, then they decide to add inland waters. But we show and we learned that everything is connected. So we don't need to have this separately. We can work together because as this demo and proof of concept show is exactly that starting from a river, we arrive to the sea. So integrate inland water with marine systems and with other solutions that are linked to the sea. So the land to sea approach is very important to be considered. And as a final conclusion, before thanking you for being here, and thanks also, put the faces of the people, please. Okay. And thank you also contributed to this, because I mean, we are those that are presenting, but behind the scene, there are more people. And so I want to thanks from engineering, Andrea and Caterina, from the CERT, to Dimitrios. Dimitrios, that they worked in WATERVERSE and CyclOps. In Setaqua, we had the support of Jordi in the preparation of the roadmap. And from CMCC, Igor worked together with Juliana probably, for the definition of for the integration of our service into EDITO. So we have. I would like to thank you for being here during this webinar, but I also want to thank all the people that allowed that this webinar has been done.
Thank you so much.
Thank you.
Thank you.
And thanks, of course, to all the speakers.
Thank you so much, Eloise, and to all of you. Thanks a lot.